any sufficiently advanced technology is indistinguishable from magic. Arthur Clarke. On the 18th of April 1955, Albert Einstein died. Newspapers reported the event and published a photograph of his desk. On it lay an unfinished manuscript. A natural question followed. What problem could be so difficult that even Einstein had not managed to solve it? The answer was the theory of everything, the dream of unifying all the laws of physics into a single framework. Even for Einstein, this goal remained out of reach. And yet, this is where the paradox begins. The meaning of the word impossible is not fixed. It shifts with time. Lord Kelvin, the most respected physicist of his era, once confidently declared that radio had no future. Heavier than air-flying machines were impossible, and X-rays would soon be exposed as a hoax. He was wrong about every single one of these claims. Ernest Rutherford discovered the atomic nucleus, yet insisted that an atomic bomb was impossible, dismissing it as chasing a sunbeam. In 1914, science fiction writer Wells published The World Set Free, a novel describing an atomic bomb. In the story, a physicist uncovers the secret of nuclear energy in 1933. 1 year earlier, in 1932, a physicist named Leo Szilard read that novel. Exactly 1 year later, he conceived the idea of the nuclear chain reaction, the realization that the energy of a single atom could be multiplied trillions of times. That idea would eventually lead to the Manhattan Project. The pattern repeats again and again. In 1921, the New York Times publicly mocked rocket pioneer Robert Goddard. An editorial claimed that he did not understand basic physics, that he failed to grasp the relationship between action and reaction, and that rockets could not function in a vacuum knowledge supposedly familiar to schoolchildren. Only one head of state truly understood the significance of Goddard's work. It was Adolf Hitler. His regime turned rocket theory into the V-2 missiles that nearly destroyed England. Even Einstein himself was not immune. In 1939, he published a paper arguing that black holes were impossible, that such objects could not exist in reality. Today, astronomers have discovered thousands of them. One sits at the very center of our galaxy. This is the crucial point. Science advances not by avoiding the impossible, but by interrogating it, by pushing against the boundaries of what seems forbidden. Today, we understand fundamental laws of nature, from the structure of a proton to the expansion of the universe. And we have also learned something else. The line between what is truly impossible and what is merely premature is far thinner than we like to believe. There is a simple rule. Everything that is not forbidden by the laws of physics eventually happens. Stephen Hawking tried to find a principle that would prohibit time travel. He failed. As a result, physicists are now forced to seriously consider the possibility of time machines. Theoretical physicist Michio Kaku, in his book Physics of the Impossible, proposed dividing the impossible into 3 categories. The first includes technologies that may become feasible within 1 or 2 centuries: teleportation, antimatter propulsion, invisibility. The second category includes technologies that may require thousands or even millions of years: time machines and travel through wormholes. The third category contains phenomena that genuinely violate known physical laws, and there are remarkably few of these. This distinction matters. When scientists say something is impossible, they often mean impossible for our civilization. For a civilization 1 million years more advanced than ours, many of today's miracles would be mundane. Carl Sagan expressed it bluntly. What does it mean for a civilization to be 1 million years old? Our technological civilization is only a few hundred years old. Our technological civilization is only a few hundred years old. We have had radio telescopes and spacecraft for mere decades. A civilization with millions of years of development behind it would be as far ahead of us as we are ahead of a lemur. So, the real question is not whether the impossible will become possible, but when. Take 3D printing. Engineers dreamed of a machine that could create objects from nothing. No molds, no casting, no machine tools. Just an idea turning directly into matter. At the time, the concept sounded absurd. Printers print on paper. Everything else requires factories, heavy machinery, and human labor. The idea was simply too far ahead of its time. In 1984, a man named Charles Hull was working for a small company in California that produced ultraviolet lamps. It was not an inspiring job, but one day, a strange thought occurred to him. What if ultraviolet light could be used to harden liquid resin, layer by layer, turning a digital model into a physical object. His colleagues were skeptical. Hull wasn't. He stayed late in the lab, experimenting with lasers and polymers. 2 years later, in 1986, he received a patent. He called the technology stereolithography. The first object he printed was a small eyewash cup. It was fragile, crooked, imperfect, but real. Hull founded 3D Systems and sold the first commercial printers for around $100,000 each. They were the size of a refrigerator, painfully slow and prone to failure. Industry reaction was dismissive. Why spend that kind of money on a machine that could only make plastic trinkets when traditional manufacturing already worked? And so, for nearly 20 years, very little happened. Then, in 2005, Professor Adrian Boyer at the University of Bath launched the RepRap project. His idea was radical and deceptively simple. Create a printer that could print itself, or at least its own plastic components. Everything else could be sourced from an electronics store. Boyer released the designs into the public domain for free. Anyone could build a 3D printer at home. That single decision changed everything. The technology escaped corporate laboratories and moved into garages, basements, and workshops. Thousands of enthusiasts around the world began improving the designs and sharing their modifications. The price of printers collapsed from $100,000 to a few hundred. Within a decade, 3D printers were being sold in ordinary stores. School children printed models for lessons. Designers created prototypes in hours instead of months. And then things escalated. In 2013, a company in China demonstrated a printer capable of producing 10 houses per day. A machine the size of a tower crane extruded special concrete, layer by layer, raising entire walls. The houses were durable and cost 70% less than conventional construction. In 2014, doctors in the Netherlands replaced a patient's upper jaw with a titanium one printed to precisely match her anatomy. She could chew, speak, and smile again. In 2016, a 3D printer was installed aboard the International Space Station. Astronauts began printing tools in orbit. A broken wrench no longer required a 6-month wait for a resupply mission. You simply downloaded the file and printed a replacement in 2 hours. In 2019, scientists in Israel printed a human heart, tiny the size of a cherry, but real, made from living cells, with chambers and blood vessels. It didn't beat yet, but that, as researchers calmly noted, is only a matter of time. The process is simple in principle. Doctors take your own cells, grow ink from them, and print a new organ. Because it's made from your cells, the body doesn't reject it. Today, companies like Relativity Space print entire rockets. 95% of their components are produced by a single massive printer, 10 times faster and far cheaper than traditional manufacturing. Designers print shoes shaped precisely to your feet. Jewelers create structures so intricate that no human hand could ever reproduce them. Complexity within complexity. In 1984, Charles Hull worked alone. His idea looked like a pointless toy. Today, the global 3D printing industry is worth $24 billion and continues to grow by roughly 20% each year. Hull died in 2024 at the age of 85. He lived long enough to see his impossible idea become ordinary. And that is the lesson that history keeps repeating. The impossible rarely disappears. It waits for time, for conditions, for one stubborn person with one unreasonable idea. Eventually, it stops being magic and becomes infrastructure. In this video, inspired by Michio Kaku's Physics of the Impossible, we'll go further into what he calls Level 3 impossibilities. You'll see how frogs levitate in magnetic fields, what scientists have already learned to teleport, whether a space elevator is feasible, what substance costs $60 trillion per gram, and why traveling faster than light is not as straightforward as science fiction suggests. Kaku has spoken with countless physicists, including Nobel laureates, and the scientific foundation here is remarkably solid. Science fiction loves force fields. Captain Kirk shouts, "Raise shields," and an invisible barrier flares into existence. Enemy fire strikes and harmlessly bounces away. In Dune, Paul Atreides activates a personal shield, and blades glance off a shimmering blue wall. Force fields feel intuitive, a transparent wall that stops everything. It almost seems like a feature a future Elon Musk might casually add to cars or robots. But reality, as usual, complicates things. And this is where the truly interesting part begins. The very idea of a physical field was born in the 19th century. A poor young man named Michael Faraday was working as an apprentice when he attended a public lecture on two newly discovered forces, electricity and magnetism. That moment changed his life and, eventually, ours. Faraday performed a simple experiment. He sprinkled iron filings over a magnet and gently shook them. The filings arranged themselves into delicate, web-like patterns. These were the field lines. To Faraday, empty space was not empty at all. It was filled with invisible structures, lines of force stretching through reality itself. In 1831, he passed a magnet through a loop of wire. An electric current appeared. The magnet never touched the wire, yet something invisible pushed the electrons into motion. Every light above your head works because of this discovery. A rotating magnet creates a field. The field moves electrons, a current flows, light appears. Albert Einstein was so deeply impressed by Faraday's intuition that he later described gravity itself using the language of fields. But here's the problem. Modern physics recognizes four fundamental forces in the universe, and none of them behave like the force fields of science fiction. Gravity only attracts. It never repels. And it is astonishingly weak. The entire Earth pulls a pen toward the floor, yet you can lift it effortlessly with one finger. Your finger overcomes the gravity of a planet weighing 6 trillion kilograms. Electromagnetism is far more powerful. It gives us light, radio, computers, and the internet, the most useful force humanity has ever harnessed. But it's easy to neutralize. Plastic passes through magnetic fields without resistance. The strong and weak nuclear forces operate only at subatomic distances inside atomic nuclei. Controlling them requires either smashing particles in accelerators or detonating atomic bombs. So does this mean force fields are impossible? Not exactly. There are loopholes. Perhaps there is a fifth fundamental force we have yet to discover. Or perhaps we can imitate the properties of a force field using clever combinations of known physics. Consider plasma, the fourth state of matter, after solids, liquids, and gases. Plasma is an ionized gas stripped of electrons, carrying electric charge. That charge allows it to be shaped and confined by magnetic fields. Almost all visible matter in the universe exists in this form. The sun is plasma. Stars are plasma. Interstellar space is filled with plasma. In 1995, physicist Eddie Gershkovich invented something called a plasma window. The device heats gas to about 6,500 degrees Celsius, turning it into plasma, then holds it in place with magnetic fields. The result is extraordinary, a transparent barrier separating vacuum from ordinary air. It is almost exactly what we see in Star Trek when spacecraft pass through invisible containment fields. And it works. Could such a barrier stop a cannonball? Possibly if it were layered. The first layer could be superheated plasma, hot enough to vaporize metal. The second layer might be a lattice of intersecting laser beams, forming a spatial grid. The third layer could be a mesh of carbon nanotube structures made of single-atom, thick carbon walls, vastly stronger than steel and nearly invisible. Such a shield would be devastatingly effective against physical projectiles. But lasers pose a different challenge. To block them, you would need materials with variable transparency, something closer to adaptive optics than armor. Sunglasses that darken instantly, scaled to cosmic levels. Science fiction often imagines force fields as effortless and universal. In Back to the Future, the hero rides a hoverboard above the ground. We don't have hoverboards, but we do have magnetic levitation. Bring the North Pole of one magnet close to another North Pole, and they repel. Maglev trains in China and Japan already exploit this principle, hovering above tracks and reaching speeds over 600 kilometers per hour. The problem is cost. These systems are expensive and energy-intensive. The key to making them practical lies in superconductors materials with zero electrical resistance. In a superconductor, electric current can flow without loss for millions of years. The catch is temperature. Superconductivity typically appears only near absolute zero, requiring costly cooling with liquid gases. In 1986, high-temperature superconductors were discovered, triggering enormous excitement. For a moment, room-temperature superconductivity seemed within reach. Progress slowed. Today's record at normal pressure is 138 Kelvin minus 135 degrees Celsius. If a room temperature superconductor were ever discovered, it would trigger a new industrial revolution. The irony is that we still don't fully understand why superconductivity works at all. That missing theory is likely worth a Nobel Prize. Superconductors have another remarkable property. A magnet placed above one will float, suspended by an invisible force. This is the Meissner effect, the expulsion of magnetic fields. Imagine highways coated in superconducting ceramics. Cars equipped with magnets would float frictionlessly above the road. Even more surprising is that levitation is not limited to magnetic materials. Water is diamagnetic. All living organisms are mostly water. That means they too can levitate in strong magnetic fields. Scientists have already levitated frogs using fields about 30,000 times stronger than Earth's. If superconductivity ever reaches room temperature, levitating large objects would become technically feasible. So no, science fiction force fields don't exist, at least not as they're imagined. But many of their properties can already be simulated. The distance between today's impossibility and tomorrow's reality is often just one insight away. And history suggests that science will eventually take that step. In Harry Potter, Harry receives an unusual Christmas gift, his father's silver cloak. He throws it over his shoulders and his body vanishes. Only his head remains, floating in the air. With the cloak, Harry roams the castle unseen, overhears secrets, and slips past danger. The idea is intoxicating. Invisibility is one of humanity's most ancient fantasies. Perseus defeated Medusa using a helmet of invisibility. Klingon ships in Star Trek disappear from sensors before striking. Frodo hides from his enemies with a ring. Plato tells the story of the Ring of Gyges. A poor shepherd finds a golden ring on a corpse in a cave. When he turns it, he becomes invisible. Power corrupts him instantly. He seduces the queen, murders the king, and takes the throne. Plato's conclusion is ruthless. Morality is fragile. Without external constraints, temptation wins. For centuries, physicists dismissed invisibility as pure fantasy. It violated optics. It contradicted the known behavior of light and matter. In the 19th century, James Clerk Maxwell finally unraveled the nature of light itself. Building on Faraday's ideas, he expressed electricity and magnetism as a set of differential equations, equations that generations of students would later fear. Maxwell asked a simple question: what happens if electric and magnetic fields continuously transform into each other? The answer was astonishing. They form a wave. And when he calculated its speed, he realized it matched the speed of light. Einstein later wrote that Maxwell's equations were the most profound and fruitful experience in physics since Newton. Maxwell's theory also explains why invisibility seems impossible. In solids, atoms are packed tightly. Light cannot pass through them like a wall of bricks. In liquids and gases, atoms are farther apart, allowing light to slip through. That's why air and water are transparent. Crystals appear to be an exception. Their atoms are tightly packed, yet arranged in a perfect lattice that allows light multiple paths. A diamond is dense and transparent. So, in principle, to make a human invisible, you would need to liquefy them, boil them into vapor, and then crystallize them again. Perfectly feasible, provided you live in a fantasy universe. The military took a more pragmatic route. Stealth technology doesn't make objects invisible to the eye, but to radar. Metal is replaced with composites. Surfaces are angled, so radar waves scatter, instead of returning to the source. It's clever engineering, but it isn't true invisibility. The real breakthrough came in 2006. Scientists at Duke University and Imperial College created something unprecedented: a metamaterial. They made an object invisible not to light, but to microwaves. Metamaterials are substances with properties not found in nature. Tiny structures embedded inside them force electromagnetic waves to take unnatural paths. Imagine a river flowing around a rock. Downstream, the water looks undisturbed, as if the rock were never there. A metamaterial does the same thing to light. Waves bend smoothly around an object and continue on their way. Everything inside becomes invisible. At Duke, researchers built a device from copper-coated fiberglass rings to microwaves. A copper cylinder placed inside effectively vanished. The trick lies in refraction. Light slows down in matter. Its path bends. In a vacuum, the refractive index is exactly 1. In air, it's slightly higher. In glass, about 1.5. In diamond, 2.4. Normally, the refractive index is fixed. Light bends once, then travels straight. But what if you could control the refractive index at every point in space? Then light would no longer move in straight lines. It would twist, curve, and flow around objects. To achieve this, the refractive index must become negative, something physics textbooks long declared impossible. In 1967, Soviet physicist Viktor Veseligo predicted such materials. The idea was dismissed as absurd. In 2006, it was realized in a laboratory. The textbooks had to be rewritten. The challenge is scale. To bend microwaves with wavelengths of a few centimeters, structures smaller than a few centimeters are enough. But visible light has wavelengths of about 500 nanometers. To manipulate it, structures must be tens of nanometers wide, just a few atoms across. That is the realm of nanotechnology. In 2007, teams in Germany and the United States built the first metamaterial for visible light. They layered glass, silver, magnesium fluoride, and silver again, then punched nanoscopic holes smaller than the wavelength of light. The result was a lattice resembling a fishing net. Red light passed through it and bent the wrong way. A negative refractive index, -0.6. This opened the door to the superlens, optics capable of imaging objects smaller than the wavelength of light itself. For the first time, it became theoretically possible to directly photograph molecules of DNA inside living cells. At Caltech, researchers use plasmonics, a technique that compresses light by coupling it to oscillating electrons on a metal surface. The wavelength shrinks, but the information remains intact. Using this approach, metamaterials with negative refractive indices for blue-green light have already been created. Progress is accelerating. Nanostructures can now be fabricated on glass, silicon, and metals. Light can be bent, focused, filtered, and shaped directly on a surface. These technologies are already inside your pocket in ultra-thin smartphone lenses and sensors. Optics are becoming flatter, sharper, lighter, and more energy efficient. Experiments with invisibility are still ongoing, but metamaterials themselves have already left the laboratory and entered real technology. And they are not the only path. There are other ways to disappear, not by bending light, but by deceiving perception. One such approach is optical camouflage. In Japan, researcher Naoki Kawakami developed a cloak covered with reflective microbeads. The system works like a living movie screen. A camera records the background behind the wearer, while a projector displays that image on the front. To the observer, the light appears to pass straight through the person. The illusion is convincing until the wearer moves. To eliminate that giveaway, the system would need holograms, not flat projections, but true three-dimensional images formed by lasers. A holographic camera captures the background. A holographic display reconstructs it in front of the body. From any angle, even in motion, the illusion holds. At that point, invisibility stops being a trick and starts behaving like a property. There is an even more radical idea, one imagined long before modern physics. In The Invisible Man, Wells proposes something stranger than optics. His invisible man does not bend light. He leaves our three-dimensional world altogether. He slips into a higher dimension, hovering above our universe like a butterfly above a sheet of paper. To the flat beings below, he simply vanishes. The existence of higher spatial dimensions has not been experimentally confirmed, and accessing them would require energies far beyond anything we can generate. But taken together, metamaterials, optical camouflage, holography, higher dimensional ideas, the trend is clear. Given the pace of discovery, some form of invisibility cloak appearing in ordinary stores within a few decades no longer sounds absurd. Now consider another impossibility. 4, 3, 2, 1, fire. The Death Star annihilates Alderaan in Star Wars. A planet vanishes in a flash. Critics laughed. A moon-sized battle station. A beam that destroys worlds. Swords made of frozen light. Even by science fiction standards, it sounded excessive. And yet, physicists have looked closely at these ideas. Surprisingly, neither a planet-destroying energy beam nor a lightsaber-like device violates the fundamental laws of physics. In fact, beams far more powerful already exist in nature. Gamma-ray bursts, cosmic explosions produced by collapsing stars, release in a fraction of a second as much energy as the sun will emit over its entire 10 billion-year lifetime. In terms of raw power, they are second only to the Big Bang itself. The dream of harnessing radiant energy is ancient. Zeus hurled lightning bolts. Thor wielded his hammer. Indra fired divine weapons of light. Archimedes was perhaps the first to seriously consider directed energy as a weapon, proposing arrays of mirrors to focus sunlight, and he understood mathematics well enough to invent a form of calculus 2,000 years before Newton. For centuries, however, physics itself stood in the way. According to James Clerk Maxwell's equations, light is a chaotic superposition of waves with different frequencies and phases. It spreads, it diffracts, it dissipates. A perfectly focused beam seemed impossible. Everything changed with the quantum revolution. By the early 20th century, it became clear that classical physics could not explain reality. Why do materials conduct electricity? Why do metals melt at specific temperatures? Why do some substances suddenly lose all electrical resistance? In 1900, Max Planck proposed a radical idea. Energy is not continuous. It comes in discrete packets quanta. In 1905, Albert Einstein took the next step, arguing that light itself consists of quanta, later called photons. He used this idea to explain the photoelectric effect, why light can knock electrons out of metal. That insight changed everything. Today, it is the foundation of lasers, solar panels, digital cameras, and the very screen you are watching right now. In 1913, Niels Bohr proposed a radically new picture of the atom. It resembled a miniature solar system, but with a crucial twist. Electrons were allowed to move only along discrete orbits. When an electron jumped to a lower orbit, it emitted a photon. When it absorbed a photon, it jumped higher. Energy, it turned out, was not continuous. It came in steps. A little more than a decade later, in 1925, quantum mechanics was born. The work of Erwin Schrödinger, Werner Heisenberg, and others showed that electrons are neither simple particles nor simple waves, but something stranger entities described only by probability. Before this revolution, atoms were mysterious and almost philosophical objects. Some scientists doubted they even existed. After it, we could calculate how particles move inside atoms and predict the properties of matter itself. In 1953, at the University of California, Berkeley, Charles Townes created the first beam of coherent radiation, not light, but microwaves. The device was called a maser. It worked by amplifying radiation through stimulated emission. The idea was so fundamental that in 1964, Townes received the Nobel Prize alongside Nikolai Basov and Alexander Prokhorov. Soon after, the same principle was extended to visible light. The laser was born. A laser works like this. At its core is a special medium, a gas, a crystal, or a semiconductor. Energy is pumped into it from the outside. Electrons absorb that energy and jump to higher orbits. The system becomes unstable. When a photon passes through, it triggers an avalanche. Excited electrons drop to lower orbits and emit identical photons. Those photons trigger more emissions. A chain reaction unfolds. Trillions of photons are released almost simultaneously, aligned in phase and direction, forming a single, intense beam. A useful analogy is a row of dominoes. At rest, they lie flat. When energy is pumped in, they are all stood upright. Push one, and the entire system releases its energy at once. Today, lasers are everywhere. In supermarket scanners, in fiber optic internet, in eye surgery, and cosmetic clinics. So why don't we have ray guns and lightsabers? The first obstacle is power. A handheld ray gun would require a battery the size of your palm with the output of a power station. With today's technology, the only devices capable of that kind of energy density are nuclear, and the smallest such device is a hydrogen bomb. It would destroy the target, the user, and everything nearby. The second obstacle is stability. In theory, there is no upper limit to the energy you can pump into a laser. In practice, the medium overheats, cracks, or explodes. A truly powerful laser would be disposable. It would destroy itself after a single shot. Light beams face a deeper problem. Light cannot be solidified. It travels at the speed of light and does not abruptly end in space. A real lightsaber made of light would extend endlessly into the sky. But there is a workaround: plasma. Superheated plasma glows and can cut steel. With a sufficiently powerful portable energy source, one could imagine a telescopic tube that injects and confines plasma, forming a blade. The physics does not forbid it. The engineering does for now. And what about the Death Star? To destroy a planet with a beam, you would need energy on an astronomical scale. To understand how that might be possible, scientists look not to weapons, but to stars. A star begins as a massive cloud of hydrogen. Gravity compresses it, heating it until hydrogen nuclei fuse into helium. A small fraction of mass is converted into energy. According to Einstein's equation, E equals mc squared. This is how stars shine. Every second, the sun loses about 4 million tons of mass, quietly converted into radiation. Scientists are attempting to harness this process, nuclear fusion, in two main ways. The first is inertial confinement. Powerful lasers focus on a tiny pellet of fuel, often lithium deuteride, smaller than a pinhead. A laser flash vaporizes the outer layer. The pellet collapses inward. Shock waves converge at the center. Temperatures reach millions of degrees. Fusion ignites. It works, but the scale is still microscopic compared to what a planet-destroying weapon would require. The second approach is magnetic confinement. Hot plasma is held in place by intense magnetic fields. This is the goal of ITER, humanity's most ambitious attempt to ignite an artificial star on Earth. In southern France, scientists are building a colossal magnetic ring designed to confine plasma at temperatures exceeding 100 million degrees hotter than the core of the Sun. The first deuterium plasma is planned for 2035. ITR is the third largest scientific project in history, after the International Space Station and the Manhattan Project. It resembles a giant donut wrapped in enormous superconducting coils. Hydrogen circulates inside. The coils are cooled to superconductivity. Vast electrical currents generate magnetic fields that hold the plasma in place. When current flows through the ring, the gas heats up to stellar conditions. Thermonuclear fusion promises something close to a miracle: cheap, clean, and virtually inexhaustible energy. The fuel could be ordinary seawater, rich in hydrogen, an energy source measured not in centuries, but in billions of years. And yet, despite decades of research, we still don't have working fusion power plants. Why? It turns out that igniting fusion is not the main problem. Sustaining it is. In the core of a star, gravity performs a perfect trick. It compresses hydrogen into an almost ideal sphere, heating it evenly and relentlessly. Fusion proceeds smoothly. On Earth, we must replace gravity with precision. Laser beams must strike symmetrically. Magnetic fields must hold plasma in perfect balance. It's like squeezing a balloon. Press from one side, and it bulges out on the other. That instability is enough to shut fusion down. Still, optimism remains. If everything goes according to plan, projects like ITER may open the door to commercial fusion reactors within the next few decades. But fusion is not the only way to harvest stellar power. Even if we fail to ignite our own artificial star, the universe is already filled with them. In 1960, physicist Freeman Dyson asked a deceptively simple question: what happens to a civilization that grows by just 1% per year? A modest rate, hardly explosive. His answer was shocking. In about 3,000 years, such a civilization would require the entire energy output of its home star. All of it. To solve this, Dyson proposed a radical idea: surround the star with a vast artificial structure capable of capturing every photon it emits. History remembers this concept as the Dyson sphere. Dyson himself did not imagine a solid shell, but a swarm, countless independent collectors orbiting the star. A rigid sphere, it turns out, is a nightmare. Every part of such a shell would be pulled toward the center by gravity. Like stones in an arch, each element would press against the next. In 1985, astronomer Michael Papagiannis calculated what material would be required to withstand that stress. Even a shell only 10 meters thick, spanning Earth's orbit, would need to be 1 billion times stronger than diamond. Such materials simply do not exist. Making the shell thicker doesn't help. It becomes so massive that it collapses under its own gravity, forming something dangerously close to a black hole. Spinning it to generate centrifugal support fails. As well, the poles would still sag inward. There is only one possible solution: make the structure unimaginably thin. So thin that sunlight itself supports it. We are talking about a surface density of roughly 1 gram per square meter, 100 times thinner than the lightest solar sail humanity has ever deployed. Such a sphere would be fragile, more like a spider's web than a fortress. A single meteorite or solar flare could tear it apart, but in return, it would solve the energy problem forever. And there's more. Such an ultra-thin shell could double as a colossal computer. Information processing woven directly into the fabric. Projects like Breakthrough Starshot are already exploring intelligent, light-driven sails where computation and structure become one. Yet even if engineering hurdles are overcome, physics still has the final word. Inside a perfectly spherical shell, gravity is zero everywhere. This is a consequence of a theorem discovered by Carl Friedrich Gauss. The star inside the sphere feels no pull from the shell. The shell feels no pull from the star. They are not bound. If the sphere drifts even slightly, the star stays put. Eventually, the star crashes into the wall and the entire structure is destroyed. It's like balancing a ball on a perfectly flat table. Any disturbance, no matter how small, breaks the equilibrium. The only way to stabilize the structure would be active control firing lasers from the shell to correct its position. But light carries very little momentum. Even a planet the size of Mercury passing nearby would introduce too much chaos. There's one more subtle problem. Enclose a star, and you change the star itself. The inner surface of the sphere reflects radiation back inward. Some of that energy returns to the star, heating it further. The star responds in the only way it can. It expands. So a Dyson sphere is not impossible, but it is nothing like the steel shell of science fiction. It would have to be a delicate, intelligent, self-correcting veil of light and computation, built in an almost empty solar system. Perhaps one day our descendants will build such a structure, or perhaps we will find one already waiting around a distant star, because any sufficiently advanced civilization will eventually face energy starvation. And when it does, the Dyson sphere stops being fantasy and becomes inevitability. Now, imagine pressing a button and vanishing not behind a wall, but across space itself. Teleportation is one of humanity's oldest dreams. Religious texts are filled with it. In the Bible, spirits carry people from place to place. In the Acts of the Apostles, Philip disappears in Gaza and reappears in Ashdod. Magicians have exploited the illusion for centuries. Rabbits from hats, coins from behind ears, entire elephants made to vanish. The trick is simple. Mirrors angled just right. Smoke, distraction. The elephant never leaves the stage. It just slips out of perception. Science fiction took the idea seriously long before science did. In 1877, The Man Without a Body by Edward Page Mitchell imagined one of the earliest teleportation disasters. A scientist discovers how to disassemble a cat into atoms and transmit them through telegraph wires. Encouraged by success, he attempts to teleport himself. The power fails. Only his head arrives. The rest is lost forever. The idea haunted writers for decades. Arthur Conan Doyle explored it in The Disintegration Engine, where a machine can disassemble a human being and reassemble them elsewhere. The inventor boasts that, in the wrong hands, it could erase entire cities at the push of a button. Horrified, the professor turns the machine on its creator and calmly walks away, forgetting to put him back together. Popular culture never let go of the nightmare. The Fly shows what happens when teleportation goes wrong. A scientist successfully transmits himself across a room, but a fly slips into the chamber. Their atoms mix. The result is a grotesque hybrid, half human, half insect. A warning etched into cinematic history. For centuries, physicists agreed teleportation was impossible. In classical physics, matter consists of tiny, solid particles, billiard balls, that move only when pushed. Objects don't vanish. They don't reappear elsewhere. Newton's universe had no room for such tricks. Quantum physics shattered that certainty. In 1925, Werner Heisenberg, Erwin Schrödinger, and their colleagues revealed something profoundly unsettling. Inside the atom, electrons do not behave like particles at all. They behave like waves, chaotic, smeared out, capable of sudden jumps between states, quantum leaps that defy everyday intuition. Schrödinger introduced the wave equation, one of the most important formulas in all of physics and chemistry. It allowed scientists, for the first time, to mathematically peer inside the atom. But it raised a deeper question. If the electron is a wave, then what exactly is waving? The answer came from Max Born. What oscillates is not matter, but probability. The Schrödinger wave does not describe where an electron is, it describes where it is likely to be found. The electron is a particle, but its behavior is governed by a cloud of probabilities. The higher the wave, the greater the chance of detecting the particle at that point. Heisenberg formalized the strangeness with the uncertainty principle. You cannot simultaneously know an electron's exact position and speed. At the quantum level, common sense collapses. Particles can disappear from one location and reappear in another. They can exist in multiple states at once. Sound familiar? As Michio Kaku once joked, if you calculate the probability that the atoms of your body might suddenly scatter and reassemble on the other side of a brick wall, you'll find that quantum mechanics does not forbid it. The probability is simply so small that you would have to wait longer than the lifetime of the universe. But the key question remains, can we use quantum mechanics to teleport something on demand? Surprisingly, the answer is yes. In 1935, Albert Einstein, together with Boris Podolsky and Nathan Rosen, tried to prove that quantum theory was incomplete. Einstein famously complained that the more successful quantum mechanics became, the more absurd it seemed. God does not play dice, he insisted. What they uncovered instead was something far stranger. If two particles are created in a shared quantum state, they can remain connected no matter how far apart they travel. Even if separated by light years, an invisible link persists between them. Change one, and the other responds instantly. This phenomenon is called quantum entanglement. Imagine two electrons born together, their spins perfectly balanced. The total spin of the system is zero. If one electron spins up, the other must spin down. Before measurement, neither spin is defined. Both possibilities exist simultaneously. But the moment you measure one electron, the wave function collapses. The state becomes real. And instantly, without any signal traveling through space, the state of the distant electron is determined as well. It looks like information is traveling faster than light. Einstein called this spooky action at a distance, and he hated it. For him, it was proof that quantum theory must be wrong. Nothing, he argued, could violate the cosmic speed limit. A decisive experiment finally put philosophy to the test. Alain Aspect and his colleagues placed two detectors 13 meters apart and measured the spins of photons emitted by calcium atoms. The results matched the predictions of quantum theory perfectly. There were no hidden variables, no classical explanation. It became clear, at the deepest level, nature is probabilistic. God, it seems, really does play dice with the universe. But there is a catch. Quantum entanglement looks like faster than light communication, yet it cannot be used to send messages. The information revealed by a measurement is fundamentally random. Knowing that an electron on the other side of the universe is spinning down is useless. You cannot encode Morse code in randomness. Think of it this way. Imagine your friend always wears mismatched socks, one red, one green. You look at one foot and see a red sock. Instantly, you know the other must be green, but you didn't send any information. You merely uncovered a correlation that was already there. For decades, this seemed like the end of the story. Then, in 1993, everything changed. A group of researchers at IBM, led by Charles Bennett, proved something extraordinary. It is possible to teleport the complete quantum information of a particle. Not the particle itself, but everything that makes it what it is. Here's the idea. Suppose we want to teleport atom A to atom C. We introduce a third atom B, which is already entangled with C. Atom A interacts with atom B, effectively scanning it. The quantum information of A is transferred to B. Because B is entangled with C, that information is instantly transferred to C as well. The result is astonishing. Atom C now possesses exactly the same quantum state that atom A had before the experiment. But there is no copying. Atom A's original state is destroyed in the process. Nature enforces a strict rule: no perfect clones. This has a chilling implication. If you imagine teleporting a human being, the original person would not survive the transfer. Their informational pattern would appear elsewhere, but the original would be gone. Teleportation, in this sense, is not transportation. It is reconstruction. After this theoretical breakthrough, a global race began. In 1997, physicists successfully teleported ultraviolet photons. In 2004, quantum states of light were transmitted 600 meters through fiber optic cables. Critics dismissed these results. They're just photons, they said. That's not real teleportation. Later that same year, the criticism collapsed. Scientists at the National Institute of Standards and Technology teleported the quantum state of real atoms. 3 beryllium atoms were entangled, and the properties of one were transferred to another. The achievement made the cover of Nature. Other teams soon repeated the feat with calcium atoms. In 2006, teleportation crossed a symbolic threshold. For the first time, a macroscopic system was involved. Researchers entangled a beam of light with a cloud of cesium atoms, trillions of them. Information encoded in laser pulses was teleported to the atomic gas across half a meter. Small by human standards, monumental by physical ones. Then came an unexpected twist. In 2007, physicists demonstrated a method of teleportation without entanglement. A beam of rubidium atoms was converted entirely into light, transmitted through a fiber optic cable, and then reconstructed as matter at the destination. Remarkably, the recreated beam retained the full quantum description of the original, including the positions and velocities of all atoms. This approach is now considered extremely promising. By 2025, similar techniques are already being used between rubidium nodes over 150-meter fibers, from Earth to satellites, and even across 30-kilometer internet cables. This is the technological foundation of the future quantum internet. So, will we ever teleport ourselves? There are no fundamental physical laws that forbid it. The obstacle is scale. Today, teleporting a single photon or atom requires the best laboratories on Earth. Teleporting a human body would require controlling and synchronizing more quantum information than has ever been manipulated in history. In reality, the fate of teleportation is inseparable from the fate of quantum computing. Both rely on the same principles. Classical computers work with bits, zeros, and ones. Quantum computers use qubits. A qubit can exist in a superposition of 0 and 1 at the same time. Imagine an atom spinning in a magnetic field. Classical intuition demands that it spin either up or down. Quantum mechanics allows it to do both simultaneously. A decade ago, quantum computers could barely perform toy calculations, like factoring the number 15 using Shor's algorithm. Today, machines from Google, IBM, and others already manipulate dozens of qubits. They solve quantum sampling problems involving numbers like 2 to the power of 80 possible states, roughly 10 to the power of 24 combinations. More possibilities than the number of seconds since the Big Bang. Classical computers can describe such spaces, but they cannot efficiently search them. Quantum machines can. Both quantum teleportation and quantum computing share the same Achilles heel: maintaining coherence. Keeping vast numbers of atoms synchronized without decoherence is one of the hardest challenges in all of science. Solving it would change everything. As David Deutsch once put it, with luck and recent theoretical advances, building a quantum computer may take far less than 50 years. It would represent a completely new way to harness nature itself. The best part of humanity will probably never perish, but will migrate from sun to sun as they fade. There is no end to life, no end to reason, and human perfection. Progress is eternal. Konstantin Tsiolkovsky. One day, far in the distant future, our last day on Earth will arrive. Billions of years from now, the sky will ignite. The sun will swell into a vast, furious sphere. Temperatures will rise beyond endurance. Oceans will boil and vanish into vapor. What remains will be a scorched world, a dry, cracked desert. Mountains will soften, melt. Becoming a two-planet species is not a luxury. It is a survival strategy, and one we should adopt as soon as possible. Earth is the only cradle of life we know, and it travels through what Sagan called a cosmic shooting gallery, a swarm of asteroids, comets, and debris. Many species before us have already lost that lottery. On shorter timescales, the dangers multiply. Over millennia, another ice age is almost guaranteed. The last one ended only 10,000 years ago. In 50 to 100,000 years, vast portions of the continents could once again be buried under kilometers of ice. On longer scales, the sun itself slowly brightens. Over the next billion years, its luminosity will increase by about 10%, enough to destabilize Earth's climate entirely. 5 billion years from now, the sun becomes a red giant. Around 7.5 billion years from now, having burned through its fuel, it will collapse into a dense white dwarf, a stellar corpse. Over cosmic time, even that will cool into a dark, inert remnant. And as if that weren't enough, there is an overwhelming probability that our galaxy will collide with its neighbor, Andromeda. The Milky Way's spiral arms will be torn apart. The sun itself may be flung into a new, unfamiliar orbit. So yes, one way or another, we will have to run. The question is not if, but how. The nearest star system lies more than 4 light-years away. Chemical rockets, the kind we use today, reach speeds of about 17 kilometers per second. At that pace, a journey to the nearest star would take roughly 77,000 years. Civilization would rise and fall many times before the ship arrived. If humanity is ever to leave the solar system, we will need a radically different kind of propulsion. There are only two options: increase thrust or increase burn time. Chemical rockets excel at short, violent bursts. A large rocket can generate thousands of tons of thrust, but only for minutes. Ion engines, by contrast, are weak, almost fragile, but they can operate continuously for years. In spaceflight, the tortoise always beats the hare. A typical ion engine resembles the inside of a television tube. An electric current heats the filament, which creates a stream of ionized atoms, such as xenon. These atoms are ejected through a nozzle. Instead of a jet of hot, explosive gas, the resulting stream is a weak but constant flow of ions. In 1998, NASA launched Deep Space One, the first spacecraft propelled by an ion engine. That engine ran for 678 days straight, setting a record. The European Space Agency tested similar technology aboard Smart 1. Japan went even further. The Hayabusa mission approached an asteroid, landed on it, collected soil, and returned powered by 4 xenon ion engines. Ion propulsion works. It is reliable, efficient, and ideal for deep space missions provided no one is in a hurry. Unfortunately, we are. Space is vast. Human lifespans are short. Waiting tens of thousands of years is not an option. This is where one of the oldest ideas in astronomy reappears: the solar sail. Light carries momentum. Sunlight exerts a tiny but constant pressure. Over time, that pressure can push a sail and everything attached to it through space. The idea goes back to Johannes Kepler, who noticed that comet tails always point away from the sun. The physics is simple, the engineering is not. In 2004, Japan successfully deployed 2 small experimental solar sails in orbit. 2 years later, another mission attempted to unfold a 15-meter sail. It partially failed. Progress has been slow, incremental, and frustrating. But then came a radical upgrade. Instead of relying only on sunlight, imagine building a colossal array of lasers on the moon, thousands of them, firing continuously at a solar sail, not meters wide, hundreds of kilometers wide. Such a sail would have to be assembled entirely in space. The laser array would need to operate for years, even decades. Its combined power output would exceed the total electrical generation capacity of modern civilization. The reward would be extraordinary. A laser-driven sail could, in principle, reach speeds approaching half the speed of light. At that velocity, a spacecraft could reach the nearest stars in roughly 8 years. No new laws of physics required, just scale, precision, and patience. Of course, the problems don't end there. How do you slow down? How do you come back? To return, you would need another laser array, this time near the destination star, or a precisely timed gravitational maneuver using the star itself to brake and reverse course. None of this is impossible, but none of it is easy. There is another option: fusion, propulsion. The universe is filled with hydrogen. A spacecraft equipped with a fusion engine could collect fuel as it travels. Scoop up interstellar hydrogen, compress it, heat it to millions of degrees, and extract energy through thermonuclear fusion. This idea was proposed in 1960 by physicist Robert Bussard. He calculated that a fusion ramjet weighing about 1,000 tons could sustain a constant acceleration of 1 g, the same acceleration you feel standing on Earth. Maintain that acceleration for 1 year, and the ship would reach 77% of the speed of light. Another way to escape Earth entirely is less explosive, but no less radical: the space elevator. The idea is deceptively simple. Anchor a cable to Earth. Extend it far into space. The centrifugal force from Earth's rotation counteracts gravity. The cable never falls. Cargo climbs along it instead of riding rockets. For a long time, this was dismissed as fantasy. No material could withstand the stress. Then came carbon nanotubes. They are many times stronger than steel, yet far lighter. On paper, supporting a space elevator is trivial for them. In 1999, NASA published a detailed study of a space elevator. The proposed design was a ribbon just 1 meter wide and about 47,000 kilometers long. Such a structure could lift a 15-ton payload directly into orbit. Today, launching a single kilogram into low Earth orbit costs roughly $4,000. A space elevator would slash that price to tens, perhaps hundreds of dollars. With the press of a button, spaceflight could cost no more than an airplane ticket. And yet, we still don't travel that way. The reason is not physics. It is materials science. We can already produce continuous strands of carbon nanotubes, meters, even kilometers long. But a functioning space elevator would require thousands of kilometers of flawless material. This is a purely technical challenge, not a conceptual one. In principle, a few decades should be enough to overcome it. But there are deeper complications. Carbon nanotubes are extraordinarily strong until they aren't. A single misplaced atom can reduce their strength by 30%. Microscopic defects become catastrophic at planetary scales. Then there is orbital traffic. Satellites in low Earth orbit constantly shift their trajectories relative to Earth's surface. Over time, any one of them could collide with the tether at speeds of 8 kilometers per second. One impact, and the entire structure could be severed. To prevent this, we would need either to equip every satellite with maneuvering thrusters to dodge the elevator, or to give the tether itself propulsion systems capable of bending it out of harm's way. Micrometeorites pose another threat. The elevator would extend far beyond Earth's atmosphere, the very shield that protects us from debris. Life on Earth survives thanks to layers of invisible protection. The ozone layer blocks ultraviolet radiation. The magnetic field deflects charged particles from the sun. The atmosphere burns up meteors before they reach the ground. In deep space, none of that protection exists. The human body is poorly adapted to this environment. In microgravity, vital minerals leach out of bones, muscles waste away. Even the most rigorous exercise programs cannot fully compensate. Prolonged weightlessness leads to muscle atrophy, degradation of the skeletal system, reduced red blood cell production, weakened immunity, and declining cardiovascular function. A journey to Mars lasting months, sometimes a year, already pushes astronauts close to their physiological limits. Interstellar missions would push far beyond them. One possible solution is artificial gravity. Future spacecraft may rotate using centrifugal force to simulate weight, but this dramatically complicates engineering and increases costs. Another danger comes from micrometeorites. Even tiny particles can be lethal at orbital velocities. Detailed inspections of space shuttle hulls revealed countless microscopic impact scars. Future starships will need heavily shielded crew compartments, layered for redundancy. And then there is radiation. Solar flares can hurl torrents of charged plasma through space. Astronauts aboard the International Space Station have repeatedly been forced to seek shelter during such events. A spacewalk at the wrong moment would be fatal. Outside Earth's magnetic cocoon, radiation becomes one of the most serious threats to human life. One radical proposal is suspended animation. Lower the body temperature until vital processes nearly stop. Some animals do this naturally. Frogs and fish freeze solid, then thaw and return to life. Their cells contain natural antifreeze. Mammals, however, are far more fragile. When human tissue freezes, ice crystals form inside cells, rupturing membranes and destroying structure. And yet, progress is being made. In 2005, researchers at the University of Pittsburgh achieved something that once sounded indistinguishable from resurrection. They revived dogs after 3 hours of clinical death. That same year, scientists placed mice in a chamber filled with hydrogen sulfide and lowered their body temperature to just 13 degrees Celsius, effectively putting them into suspended animation. In 2019, surgeons performed deep hypothermia on a human patient for the first time, temporarily stopping blood circulation to buy precious time after fatal injuries. In 2023, using ultrasound, scientists learned how to induce hibernation in mice and rats for an entire day. The trajectory is clear, but the timescale is unforgiving. It will take decades before such techniques can be applied to astronauts, and centuries before humans could safely remain in suspended animation for interstellar journeys. Sending people to the stars is not a mission. It is a trial by physics, biology, and patience. Human starships would have to be colossal machines, consuming absurd amounts of energy just to keep their passengers alive. There is a more realistic first step. Instead of sending humans, we can send machines, miniature ones. As nanotechnology advances, we gain the ability to build spacecraft on atomic and molecular scales. Tiny probes, lighter than dust, Ions have extremely small mass and can be accelerated to enormous speeds with relatively modest energy. In the vacuum of space, there is no friction. Once accelerated, nothing slows them down. Engineer Gerald Nordley proposed a radical idea. Place an ionized nanobot in an electric field and it will be flung toward the stars. The same fields can apply pressure to microscopic solar sails, accelerating them even further. In principle, a constellation of pinhead-sized spacecraft flying in formation and communicating with one another could be accelerated using something as simple as a powerful flashlight. The concept is elegant. The problems are subtle. Nanostarships are vulnerable. Electric and magnetic fields in space can deflect them. Many would miss their targets entirely. To compensate, they would need to be launched in vast numbers, millions, perhaps billions, just to ensure that a fraction arrive. It sounds wasteful until you remember that these machines would be cheap. Mass production changes everything. Former NASA Administrator Daniel Golden imagined fleets of spacecraft no larger than a soda can. Others envision probes the size of needles. The Pentagon has explored the concept of smart dust, microscopic devices equipped with sensors and computation. Such probes could be launched from the moon using railguns or particle accelerators. Once a probe reaches another star system, it doesn't need to return. It lands on a barren moon where gravity is weak and resources are abundant. Using local materials, it builds a nanofactory. The factory constructs a powerful radio transmitter and sends data back to Earth. Then it does something even more important. It builds copies of itself again and again and again. This idea is known as the von Neumann probe, named after John von Neumann, who first described self-replicating machines. Such probes could spread through the galaxy at a significant fraction of the speed of light. Over time, a growing sphere of trillions of machines would form, exploring star systems, mapping planets, harvesting information. In a few 100,000 years, a blink of an eye, on cosmic timescales, they could traverse the entire Milky Way. The laws of nature guarantee that Earth will one day perish, but those same laws also say something else. Escape is possible, difficult, dangerous, expensive, but possible. Humanity faces a choice: stay and eventually disappear, or go and endure. And if we are to go, we will need energy on a scale that still feels obscene. In Angels and Demons, extremists plot to destroy the Vatican using an antimatter bomb stolen from CERN. The idea feels exaggerated until you look at the physics. When matter meets antimatter, both are converted entirely into energy. No residue, no inefficiency. A nuclear bomb converts about 1% of its mass into energy. An antimatter bomb converts 100%. At the beginning of the 20th century, physicists discovered that atoms are not indivisible. Electrons, negatively charged particles, orbit a tiny, positively charged nucleus. That nucleus contains protons and neutrons. It became clear that nature is even more symmetrical. Every particle has a twin, an antiparticle identical in every way except charge. The first discovered was the positron, a positively charged electron. In 1955, the first antiproton was created at a particle accelerator in Berkeley. Combine them, and you obtain an antiatom, positrons orbiting an antiproton nucleus. In theory, every element has an antimatter counterpart: anti-hydrogen, anti-carbon, anti-iron. And then the questions spiral outward. Could there be anti-humans, anti-planets, entire anti-worlds, or even anti-universes? In 1995, CERN caused a scientific sensation. Researchers announced the creation of 9 atoms of anti-hydrogen, just 9. And yet this tiny achievement carried a staggering implication. Nothing in the laws of physics forbids the creation of heavier anti-elements. The obstacle is not theory, it's cost. An absurd cost. In 2004, CERN calculated that producing mere trillionths of a gram of antimatter had cost around $20 million. At that rate, a single gram would require $100 quadrillion and roughly 100 billion years of continuous operation. No economy could survive that. CERN itself once summarized the situation with brutal honesty. If we gathered all the antimatter ever created and annihilated it with matter, it would power a single light bulb for a few minutes. Handling antimatter is no easier than producing it. Any contact between matter and antimatter results in instant annihilation. A conventional container is useless and lethal. The only solution is to ionize antimatter into a gas and trap it inside a magnetic bottle. Magnetic fields prevent it from touching the walls. One mistake, and the container becomes a bomb. At first glance, antimatter seems like the most expensive and useless substance ever created. It costs more than entire nations and threatens to explode at the slightest error. Why pursue it at all? Because antimatter is the most efficient fuel imaginable. An antimatter engine would work by feeding a steady stream of antimatter into a reaction chamber, where it gently meets ordinary matter. The annihilation releases enormous energy. The resulting ions are directed through a nozzle, producing thrust. In theory, this is the most powerful engine allowed by physics. In Star Trek, the Enterprise travels exactly this way. One of the most passionate advocates of this idea is physicist Gerald Smith of the University of Pennsylvania. His calculations are startling. Just 4 milligrams of positrons could propel a spacecraft to Mars in a matter of weeks. Weeks instead of 9 months, the timeline targeted by modern chemical rockets. Smith points out that antimatter releases roughly 1 billion times more energy per unit mass than conventional rocket fuel. The problem is production. Today, antimatter is made using particle accelerators built for fundamental research, not manufacturing. They are wildly inefficient. Smith dreams of a dedicated antimatter factory, an accelerator designed specifically to mass-produce antiprotons. He is convinced that antimatter engines will one day power interplanetary and perhaps interstellar travel. But this raises an obvious question. If antimatter is so hard to produce on Earth, wouldn't it be easier to find it in space? Surprisingly, we haven't. This absence is one of the deepest mysteries in cosmology. At the birth of the universe, matter and antimatter should have formed in equal amounts. If that were true, they would have annihilated completely, leaving behind nothing but radiation. And yet, here we are. The most compelling explanation was proposed by Andrei Sakharov. He suggested that in the earliest moments after the Big Bang, a tiny asymmetry emerged, slightly more matter than antimatter. Almost everything annihilated. What remained, a minuscule surplus of matter, became galaxies, stars, planets, and us. Every atom in your body is the fossil of that primordial catastrophe. This theory leaves open one tantalizing possibility. Small pockets of antimatter may still exist in nature. If such reserves could be found, the cost of antimatter fuel would collapse overnight. There have been hints. William Purcell of Northwestern University reported what appeared to be antimatter fountains near the center of the Milky Way. In 2006, the Pamela satellite was launched to search for antihelium, a signature of antistars. It found none. Still, the idea refuses to die. NASA Institute for Advanced Concepts has seriously explored the possibility of harvesting antimatter in space. One proposed design resembles a cosmic fishing net. 3 concentric wire mesh spheres form the core. The outer sphere, 16 kilometers in diameter, carries a positive charge, repelling protons while attracting antiprotons. Passing through successive layers, the antiprotons slow down and are gently captured by magnetic fields. There, they are combined with positrons. Antihydrogen is born. Controlled annihilation could, in principle, push a solar sail spacecraft all the way to Pluto using just 30 milligrams of antimatter. Reaching Alpha Centauri would require roughly 17 grams. By cosmic standards, that's almost nothing. By human standards, it's impossibly expensive. Given the technical challenges and the cost of deploying a colossal antimatter collector in space, such a project is unlikely to be realized before the end of the 21st century, if not much later. The story of antimatter itself begins long before rockets and starships. In 1928, one of the most brilliant physicists of the 20th century, Paul Dirac, made a discovery that would quietly reshape reality. Dirac held the Lucasian chair at Cambridge, the same position once occupied by Isaac Newton. He entered physics at the height of the quantum revolution. Scientists knew that particles like electrons behaved not only as objects, but also as waves, described by Schrödinger's equation. But Dirac noticed a fatal flaw. Schrödinger's equation worked only for slow electrons. At high speeds, it broke down. It violated Einstein's relativity. Dirac set out to fix this, to build an equation that respected both quantum mechanics and special relativity. In 1928, he succeeded. The result was elegant, terrifying, and revolutionary. Along the way, Dirac discovered something even more disturbing. Einstein's famous equation, E equals mc squared, turned out to be incomplete. The correct expression was equals plus or minus, a plus sign and a minus sign. The mathematics demanded it. Taking a square root leaves two solutions, and that raised a terrifying question. In physics, systems always seek the lowest possible energy. But what happens if negative energy exists? If electrons could fall endlessly into lower and lower negative states, the universe would collapse in an instant. Dirac's theory seemed to predict instability at the most fundamental level. To save reality from destruction, Dirac proposed an audacious idea. He suggested that all negative energy states are already filled, completely occupied. This invisible ocean became known as the Dirac Sea. Because every negative state is filled, ordinary electrons cannot fall into them. The universe remains stable. But occasionally, something strange happens. A high-energy gamma ray strikes the sea and knocks one of these hidden electrons into a positive energy state. The electron appears, and what's left behind is a hole, a vacancy in the sea. This hole behaves like a particle. It has the same mass as an electron, but the opposite charge, an anti-electron. In other words, antimatter is not something exotic added to the universe. It emerges naturally from the structure of quantum theory itself as bubbles in an invisible sea. A few years later, this prediction was spectacularly confirmed. Carl Anderson discovered the positron in cosmic ray experiments. In 1933, Dirac received the Nobel Prize. His equation had not only predicted antimatter, but also explained electron spin, an intrinsic quantum property essential for understanding transistors, semiconductors, and all modern electronics. Stephen Hawking later remarked that if Dirac had patented his equation, he would have earned royalties on every television, computer, and video game ever built. Dirac never did. Today, his equation is engraved in stone at Westminster Abbey, near Newton's grave. But Dirac's legacy goes far beyond technology. His theory opens questions that still haunt physics. How does gravity behave for antimatter? Antiparticles carry opposite electric charge, but gravity doesn't care about charge. Some particles, like photons and gravitons, are their own antiparticles. This suggests a profound conclusion. Gravity and anti-gravity are the same thing. Antimatter falls down, just like matter. Every physicist agrees, though the experiment has yet to be performed directly. Which leads to the deepest question of all. Why does antimatter exist at all? And if nature allows it so effortlessly, could entire anti-universes exist somewhere beyond our cosmic horizon? Science fiction writers have been fascinated by this idea for decades. A hero stumbles upon a planet almost indistinguishable from Earth. Cities, streets, people, children, everything looks familiar. There is only one difference. The planet is made entirely of antimatter. Every human there has a perfect counterpart. Anti-people raise anti-children in anticities. Chemistry works exactly as it does here. Reactions proceed normally. Atoms form molecules. Life unfolds as usual. The only distinction is invisible. All charges are reversed. To the inhabitants of that world, nothing feels strange. To them, reality is perfectly ordinary. Physicists call this a reverse charge universe. There is another, equally popular idea, a mirror world. A twin Earth where left and right are swapped. Hearts beat on the right side of the chest. Left-handed people are the majority. Even the spiral of DNA twists the other way. Such a place is known as a mirror universe. It sounds exotic, but at first glance, physics doesn't forbid it. Newton's equations still work if you reverse all charges. Einstein's equations remain valid if you swap left and right. Then Richard Feynman proposed a thought experiment that changed everything. Imagine we establish radio contact with an alien civilization. We can hear them, but we cannot see them. Explaining our biology is easy. The number of fingers, the structure of atoms, the laws of chemistry, all of this can be transmitted with equations. But now try explaining something deceptively simple. Left and right. Or clockwise and counterclockwise. It turns out to be impossible. You can't define which side your heart is on, which way the Earth rotates, or how the DNA helix twists without already sharing a reference. For a while, it seemed that mirror universes were perfectly plausible. And then nature intervened. In the 1950s, two physicists, Tsung-Dao Lee and Chen-Ning Yang, demonstrated something shocking. By studying radioactive decay, they proved that nature itself distinguishes between left and right. Certain particles violate mirror symmetry. This phenomenon is called parity violation. The universe, at a fundamental level, has a preferred handedness. For this discovery, Lee and Yang received the Nobel Prize in 1957. Suddenly, Feynman's problem had a solution. We could explain left and right to aliens. Before meeting them, we'd agreed to perform a simple experiment with radioactive particles, the kind that unambiguously reveal handedness. Then we'd meet the aliens and ask them to extend their right hand for a handshake. If they extend their right hand perfect, we understand each other. But what if they extend their left? That would mean either we explained it badly, or they are made of antimatter. And that second option is far more disturbing. In an antimatter world, radioactive experiments would yield opposite results. Left and right would be flipped at a fundamental level, and if we tried to shake hands, matter and antimatter would meet. There would be an explosion. So no, a perfect anti-Earth indistinguishable from ours cannot exist. Even reversing both charge and mirror symmetry isn't enough. Nature still finds a way to tell the difference. This was confirmed in 1980, when James Cronin and Val Fitch discovered CP violation. The universe breaks symmetry even more deeply than anyone expected. Many physicists were disappointed, but this asymmetry is the best news we could possibly have. If symmetry were perfect, the Big Bang would have created equal amounts of matter and antimatter. They would have annihilated completely. No atoms, no stars, no planets, no people. We exist because symmetry is broken. Does that mean anti-universes are impossible? Not entirely, but they would have to be far stranger than science fiction imagined. To create a fully self-consistent mirror world, three things must change at once. Charges must be reversed, left and right must be swapped, and time itself must flow backward. Only then do the equations still work. In such a universe, dropped eggs leap off the floor, reassemble, seal themselves, and return to the hand. The dead grow younger, rivers flow uphill, causes follow effects. From our perspective, it looks absurd. Common sense rebels, and yet mathematically, such a universe is allowed. But communication would be impossible. If time flows backward there, any message we send would arrive as the past. The moment they receive it, they would instantly forget it. No handshakes with aliens. So where does this leave us? We exist because matter won over antimatter by the tiniest margin. Somewhere out there, small regions of antimatter may still survive. If we ever find them, they would be the ultimate fuel, the most efficient energy source imaginable. With antimatter, the stars become reachable. Nothing would stop us, except one thing, the speed of light. Or is that limit absolute? Astonishingly, the answer is no, but that's a story for another time. Traveling faster than light is impossible, and besides, it's pointless. The hat flies off too often. The Millennium Falcon lifts off from a desert world. Imperial cruisers close in. Laser fire slams against the shields. They're failing. Han Solo doesn't hesitate. Hyperspace is the only chance. 1 second. Engines ignite. The stars stretch into blinding lines. Space tiers open into a glowing tunnel, and the ship vanishes. Einstein gave us a brutal rule. The speed of light is absolute. Nothing can outrun it. No engine, no particle accelerator, no amount of energy. Light is the universe's traffic cop, stopping every would-be violator. If that rule is final, then interstellar dreams collapse. Galaxies remain forever out of reach. But physics has never been about accepting limits quietly. For decades, physicists have searched for loopholes. Most are trivial. Yes, you can sweep a flashlight across the sky faster than light, but no information travels that way. It's meaningless. A trick, not an escape. The most interesting loophole was found by Einstein himself. In 1915, with general relativity, he revealed that space and time are not rigid. They are a fabric elastic, stretchable, compressible, and sometimes that fabric can expand faster than the speed of light. This already happened once. At the birth of the universe, during the Big Bang, space itself expanded faster than light. Nothing violated relativity, because nothing was moving through space. Space itself was changing, and that changes everything. Because if space-time can stretch and bend, it can also be engineered. General relativity allows two radically different ways to outrun light without breaking the rules. The first is to move space itself. If space behind a ship expands while space ahead of it contracts, the ship doesn't move at all. Locally, it's at rest, but the distortion carries it forward. From the outside, it appears to travel faster than light. This idea is known as the Alcubierre drive. Proposed in 1994, it's essentially the warp drive of Star Trek. The ship sits inside a bubble. Inside, physics is normal. No crushing forces, no time dilation, no violation of causality. Outside, spacetime is violently distorted, stretched behind, compressed ahead. The ship rides the wave. The price is extreme. Calculations show such a drive requires negative energy or negative mass, not antimatter. Antimatter has positive mass and positive energy. Negative matter would be something far stranger. Lighter than empty space, repelled by gravity, fleeing stars instead of falling toward them. If it exists at all, it would hide in deep interstellar voids. Certainly not on Earth. Negative energy, however, does exist in tiny amounts. In 1948, it was measured indirectly, and its origin lies in something even stranger: the vacuum. In 1933, Hendrik Casimir predicted that two uncharged metal plates placed close together would attract each other. No wires, no forces, just empty space. The reason? The vacuum isn't empty. It boils with virtual particles popping in and out of existence, and under special conditions, this quantum vacuum contains negative energy. The problem is scale. The Casimir effect is unimaginably weak. Extracting enough negative energy to move a starship would require engineering beyond anything we can currently imagine. There's another catch. A warp bubble isolates its interior from the outside universe. No signals can enter. No commands can be sent once the journey begins. Direction and destination must be calculated in advance. Warp travel wouldn't be free flight. It would be rail travel. Predetermined routes through spacetime, followed like cosmic train schedules. The second faster-than-light option is even more dramatic. Don't stretch space, punch through it. In school, we learned that the shortest distance between 2 points is a straight line. That's only true in flat space. Fold the space, and two distant points touch. The shortcut is called a wormhole. The idea emerged from Einstein's equations themselves. In 1916, Carl Schwarzschild found a solution that revealed something horrifying at the center: a black hole. Later, in 1963, Roy Kerr showed that a rotating black hole doesn't collapse to a point, but to a ring. Pass through that ring, and in theory, you emerge somewhere else. Another region of space, another universe. But black holes are one-way doors. Cross the event horizon, and you can never return. In 1988, future Nobel laureate Kip Thorne and his colleagues did something extraordinary. They calculated a traversable wormhole, one that could, in principle, be crossed safely in both directions. In one of their solutions, passing through a wormhole would be no more dangerous than boarding an airplane. No spaghettification, no instant death, just a shortcut through the universe. But physics never gives gifts without sending an invoice. To hold open a wormhole just 1 meter wide would require an amount of negative energy comparable to the mass of Jupiter. Not ordinary energy, negative energy, something we can barely measure, let alone store. And even if such energy were available, stability remains an open question. Wormholes might flood travelers with lethal radiation, or collapse the moment something enters them, or simply refuse to stay open at all. There's another obstacle, even more fundamental. To tear spacetime apart in the first place, you'd need to concentrate energy on the scale of the Planck energy, a quadrillion times greater than anything humanity can currently achieve at the Large Hadron Collider. At these scales, space itself is believed to foam. Quantum fluctuations create microscopic bubbles that flicker into existence and vanish instantly. Some physicists suspect that if enough energy were injected into a single point, one of these bubbles could expand, and that bubble would be a wormhole, a bridge to a newborn daughter universe. From everything we know today, stretching space or tunneling through it appear to be the most realistic ways to outrun light. We still don't know whether these structures can be stabilized. And even if they can, the energy demands are almost obscene. Perhaps some advanced civilization somewhere in the cosmos has already mastered such power. But for us, this lies thousands, maybe millions of years ahead. Breaking the light barrier is not forbidden. It's a second-class impossibility, allowed by the laws of physics, but far beyond our current reach. Someday, perhaps, our descendants will compress space ahead of their ships and stretch it behind them. They will carve tunnels through space-time itself. For them, the universe will no longer feel vast. It will feel small. History gives us a warning against arrogance. In 1894, Nobel laureate Albert Michelson declared that physics was essentially finished. All the fundamental laws had been discovered, he said. Future work would amount to polishing decimals. He said this just years before quantum mechanics and relativity shattered the foundations of classical physics. In 1825, the philosopher Auguste Comte compiled a list of things humanity would never know. We would never discover what stars are made of. We would never understand the deep structure of matter. We would never apply mathematics to biology or chemistry. You already know how that turned out. Today, new lists of impossibilities are being written. We will never know what came before the Big Bang. We will never build a theory of everything. We will never fully understand reality. Physicist John Wheeler responded to such claims with a simple insight. 2 centuries ago, if you asked whether humanity could ever understand the origin of life, the answer would have been an obvious no. Wheeler believed the same about the origin of the universe. Statements of impossibility are not final verdicts. They are challenges, invitations, markers placed precisely where progress is about to begin. There will always be limits, quantities we cannot measure exactly, phenomena we cannot directly observe, worlds we cannot yet reach. But the laws themselves, Wheeler believed, are finite and knowable, and the coming decades may be the most exciting in the history of physics. New particle accelerators, space-based gravitational wave observatories, technologies we haven't yet imagined. We are not at the end of the road. We are standing at the threshold of a new physics, and whatever we discover, new horizons will inevitably rise beyond it.